All right, let's work another example. This time we're going to once again use a transformer with a turns ratio right here. That's A of 3:1. And when it says the Thevenin equivalent impedance, what it means is that these two are a box, and that is like Z Thevenin. Remember, a Thevenin equivalent circuit has one voltage source and one impedance. Well, we got 100 volts angle 0. That's like an E Thevenin. And then the Z Thevenin is one equivalent impedance, 36. This would be like a minus J54. And then what we're going to do is everything on the right is going to be like our Thevenin load. Our Thevenin load, which is also our reflected impedance. Okay, so what load impedance must be chosen to ensure that the maximum power transfer occurs? Remember, we get max power if the Z Thevenin load equals the Z Thevenin complex conjugate. You may be thinking, wait, what's the difference between the load that's written over here and the Thevenin load? So this right here is the Thevenin load. This load is not the Thevenin load. It's my actual load. What is the Thevenin load? If I had my circuit where I had a Thevenin impedance and I had a Thevenin load over here. So we'll call this Z load Thev, just to be clear. That's my Thevenin load. And what I'm doing is I'm taking this Thevenin load, and that is my reflected impedance. So if I want my max power, then my Z Thevenin is 36 minus J54. So 36 minus J54. And I need the complex conjugate of that. So I need 36 plus J54. As far as this Thevenin circuit is concerned, what it's saying is we have a resistor and a capacitor. And if we want max power, then we want a resistor and an inductor. And if this has minus J54, then down here I want positive J54 to make it a purely resistive circuit. And that purely resistive circuit will produce max power. So if I want this as my Thevenin load, and what I'm doing is I'm setting everything inside my red box up there as my Z primary reflected. That reflected impedance, as far as the source can tell, I'll put this down in a box. My red boxes match as far as my primary side. Yes, that's kind of pink. My pink boxes match. So if I want to set that Z primary reflected is A squared Z secondary, what this really is, this is like up top, this is my Z secondary. I could call it my Z secondary because everything that's on that secondary side is in what they're calling that load. Not the Thevenin load, just the load they have. So if I take that 36 plus J54, my A squared is 3 squared Z secondary. Then Z secondary would be divided by 36. Here, I'll go ahead and do it. 36 plus J54 divided by 9, and I get 4 plus J6. And so I need to set what's inside of this yellow. It's like I need that in order to achieve max power. So the actual circuit, if this is an equivalent circuit, this is my Thevenin equivalent on this side, my actual circuit would have a resistor, a capacitor, the transformer, and it wants a resistor and an inductor of 4 and 6 ohms. Right here is that R, and right here is the XL, because it's a positive J. And so this transformer is still here, and if I have it as 4 and 6, then it produces this over here as a model of my Thevenin equivalent. And it says, what is the transformer load VA of this for this value of the Z load? So what I can do here is I can look at the S equals VI, and it just wants the apparent power, which I can take just those. My apparent power is just the magnitudes of V and I. And the transformer load for this value of Z load. Actually, you know what? I think we'll do it with the complex conjugate as the complex power, because it helps us a little bit more in the long term as we try to solve this. So if I'm looking for what's across the transformer, and the transformer, that's like saying the V primary and the I primary. And right here between these green dots, that across there, we've treated it as the reflected impedance, but between those green dots, that is right here, the reflected impedance, and that is across the transformer. So if I can find the voltage from those green dots, actually I'll just highlight it in green here too. Okay, so that if I can find the voltage across that, that is my V primary. If I can find the current going through that, that is my I primary. So I'm going to use my V primary, and this is back kind of just Thevenin and simple series circuits. I'm going to use VDR to solve for that. And so the V primary is 100 volts, angle 0. And what I have up top is I want to know my 36 plus J54. And then on the bottom, my J54s cancel out, and I'm just left with 72, right? If this is my total inside of that little series circuit, and that V primary comes out to 90.138 volts, angle 56.3 degrees. I can find the I primary in this little Thevenin circuit. I primary is V total over Z total, right? Because this is the I total on this side. Everything inside of this has the same current. So the V total is 100 volts, angle 0, divided by just the 72, because the J54 and the negative J54 canceled each other out. And what I get there for my I primary is 1.389 amps, angle 0. And so now I can plug both of these together. 90.138 volts, angle 56.3. Actually, let's bump that down here. And we multiply that voltage by the current, 1.389 amps, angle 0. And what I come out to for the S across my transformer, S complex power, is 125.2 volt amps, angle 56.3 degrees. And if I wanted to just say the apparent power S is just the 125.2 volt amps. So there is part B. And part A was right here, boxing that answer, 4 plus J6 ohms. If you're thinking to yourself, man, I thought there would be another way to solve for S equals VI, or, V squared over Z, I squared Z, go for it. You should get this same answer. And if not, let's talk about it in class about where the mistakes happen in. But there's multiple ways to get to the complex power. Feel free to use any of the formulas on the equation sheet to do so.